Swayam Prabha. Digital India. Educated India.
Hello everyone, this is lecture 2 of module 10. In the module 10, we have been discussing about brief on earthquake geodesy. So this is basically the science of deformation, measuring deformation due to the earthquake of a fault. It may be the co-seismic deformation, or maybe the interseismic, or maybe the pre-seismic deformation. And the lecture 2 will consist of the discussion on co-seismic deformation. And in the lecture today, we are going to cover the concepts such as the co-seismic deformation, and then we will have a topic that is dependent upon the static displacement due to strike slip fault, and then we will see how the static displacement of infinite fault is calculated. Then we will discuss about the finite fault, and then we will talk about the buried fault, and then finally we will talk about the static displacement due to dip slip fault. As far as the recap of previous lecture is concerned, we said that the geodetic methods using the signals from the space can be used to compute all three components of position to be measured to sub-centimeter precision. And there are some popular techniques for the geodetic data to measure ground deformation. First one is the very long baseline interferometry. In short, it is known as VLBI. Second one is satellite laser ranging, that is in short known as SLR. And then the most popular one is the global positioning system, that is GPS. And in GPS, we generally use the constellation of satellites that transmit coded timing signals on a pair of microwave carrier frequencies that are synchronized to very precise onboard atomic clocks. GPS data can be collected in two modes. One is the continuous data, another is the survey mode data. In the continuous mode, we continuously record the data by keeping the GPS instrument onto a place for maybe months or maybe the years, and then there is another mode that is known as survey mode, in which we keep the instrument for a short period of time, then we revisit the place after some time. The second mode, that means the survey mode, is considered to be cheaper. The biggest limitation for geodetic data for earthquake studies is that the position of the geodetic marker before the earthquake are known. That means you should be having some idea about the location of the incoming earthquake. Maybe you can install your GPS in an area which is relatively active, maybe seismic region such as the northeastern India, where so many thrust faults are there, and it is known to have a lot of earthquake in the past history. Likewise, there are several other regions where you can install, but it is considerably challenging to install such instrument in the region where the seismic activity is not that prevalent. So in that case, you will have to do some kind of survey, or maybe you will have to place the instrument at a place where the network of fault is there. Then we learnt about the radar, where the D is the antenna length and R is the altitude to the radar from the surface of the earth, and X is the size of the object that we would like to resolve. So in that case, theta D will be equal to lambda by D, that is equal to X by R, where lambda is the wavelength and D is the antenna length, X is the size of the object, and R is the altitude from the surface of the earth to the radar. The phase difference between the radar signals with wavelength lambda reflected from the Earth's surface and recorded by antennas at position A1 and A2 is calculated by this formula, where phi is equal to 4 pi by lambda in bracket R2 minus R1, and Ri is the range from antenna at AI to the reflection point. If differences in satellite position between the measurement are removed, a vector surface displacement cause a phase change, and that will be approximately equal to 4 pi by lambda delta r. This is just the variation of this formula, and since we are having the very minute differences in the satellite position, so it has been replaced with delta r, and delta r is the d dot r cap, where delta r is the projection of the vector displacement along the loop direction connecting the satellite and the reflection point. Let's start with the today's lecture. Here we are going to first discuss about co-seismic deformation, and the co-seismic deformation, where the static co-seismic displacement occurs. The radiation pattern of the co-seismic displacements from the earthquakes are considered to be similar to the propagating seismic wave displacement. So, static co-seismic displacement can be used to provide important information about the fault geometry and the slip on the fault. If we talk about the attenuation or maybe the reduction in the displacement of the static co-seismic displacement, that decays as 1 by r square, while on the other hand the seismic propagating wave decays as 1 by r, that is for the propagating wave. So you can see that the co-seismic displacement, static co-seismic displacement, decays relatively faster with distance from the earthquake. So that is why we typically describe the static displacement using Cartesian coordinates near a fault instead of the spherical coordinate that is used for the teleseismic waves. If you look at these figures here, these are the static displacement for 1927 Tango, Japan earthquake, which was of magnitude 7.5. And here you can see there are the several vectors that are being shown here. The direction here is on the up direction, and here it is going in this direction. And this is the trace of the fault here that is being shown by the dashed line. And you can easily understand just by looking at these directions that the fault is of left lateral strike slip fault. And the figure on the right is basically displaying the displacement that is decaying rapidly with distance from the fault. So basically, if you go away from the fault in this direction, you can see the length of the vectors are reducing, and here also the length of the vectors as you go away from the fault location in the perpendicular direction, the magnitude of the vectors are basically reducing. So this is what it is representing here. And the northeast direction, that means in this direction, as you go away from the fault, the displacement is reducing, and here also in this direction, since we are taking the opposite direction here, so it is all considered over here in the southwest direction, and it is decaying something like this. And the x-axis is basically representing the distance from the fault in kilometers. So this is what it is written. This basically shows an example of the static displacement of 1927 7.5 magnitude Tango, Japan earthquake. The displacement changed direction across the fault. Displacement directions show that the earthquake involved left lateral strike slip fault. The right figure here shows the displacement decays rapidly with distance from the fault. Now let's talk about the static displacement due to slip on the fault, that is of infinite fault, and it is basically sometimes complicated to derive static displacement due to slip on a fault. And in order to have just an idea about it, let's talk about an example of pure strike slip faulting on an infinitely long vertically dipping fault such as this one. You can see the shaded portion is representing the fault plane, or you can say the fault surface, and here L is the length of the fault, W is the width of the fault. W is basically the depth to which the faulting extends, and it is, we are calling as the fault width. And in this particular diagram, you can see the displacement, the static coseismic displacement are decaying as you go away from the fault surface. So basically the y direction is representing the distance from the fault, either in this direction or in this direction along y, and the slip is basically happening along x direction. So this particular diagram is showing the displacement from the fault as a function of distance, that is in y direction, for three type of fault width, that is in kilometers, for 5 km, for 20 km, for 30 kilometers. So you can see here all are basically reducing, or you can say those are getting reduced as you go away from the fault plane or fault from the location of the fault. The fault parallel displacement in x direction, that is uy, that varies with the distance from the fault ys. This is the formula or the expression of the displacement, that is uy, that is varying with distance from the fault as y. So you can see that d is basically the dip across the fault, and y is the distance from the fault, and w is the width to which the faulting extends, cause that is also called as faulting width. And d is positive and negative, that depends upon y. If y is greater than 0, that means if you are going in this direction, then d we are considering positive. If we are going in this direction, then d is negative. We are also having an assumption for this coseismic static displacement formula here, the expression, that the slip is uniform all across the fault plane. So just take this formula again and look at it, and you can see near to the fault, that means when y is tending to 0, that means y is 0, almost 0, that gives the displacement plus minus d by 2, because y is 0 here, so this all will become 0 and uy will become plus minus d by 2. The displacement decays away from the fault. For example, when y is equal to capital W, that means the distance is almost equal to the width of the fault, then the uw will be d by 4. That means when you are starting from near to the fault location and going away and reach to the distance that is equal to the width of the fault, then you will see the displacement, that is d by 4, that is almost half of what you have seen near to the fault. Far from the fault, the y by w will tend to 0, or the displacement will die off. That means the displacement will become almost 0 as you go very far away from the fault location. Hence, the distance over which the displacement extends give information about the fault width. So you can easily say that when the displacement will become almost half of what you are getting near to the fault surface, then you may think of that distance may be equal to the width of the fault, and it is basically giving the information about the fault width. For this infinite fault, since the fault is extending to the in depth to the infinite length, so we are considering that it is an infinite fault. The fault parallel displacement extend to infinity along the fault. So you can see the fault is extending infinity up to infinity in this direction, or maybe in this direction, in both direction. And then if you are taking an example of finite length fault here, then in that case, this is the example which is shown. It is saying that these are the contour line that for the displacement, static coseismic displacement for the finite fault that are drawn here. And you can see that as you go further away from the fault, then you can see the labels on the contours are basically reducing. That basically represent that the displacement are reducing as you go away from the fault location. Likewise here also it is happening the same way. And this is the picture that shows the decay of the displacement that depends on the ratio of the fault width to the fault length, that is W by L. Thus, the fault width estimated from decay depends on the assumed length. So you can see here it is 2.5 W by L, and here it is 5, and here it is infinity. So as you increase it, then you can see almost in all the cases the displacement is decaying away as you increase the value of a small y to W. That means the distance divided by the width of the fault. And if you are talking about a buried fault, buried means, let's suppose this is your surface and it doesn't have any exposure onto the surface. That means the fault is buried. It is not seen on the surface. So in that case, you can consider that the depth at which the fault has, the depth of the fault is around small w, and in that case the fault is buried and extends from depth W to depth capital W, then displacement is given by this expression. In this case, the maximum surface displacement is less than half the fault slip and occur a distance from the fault equal to the mean depth, that is W capital W to the power 1 by 2. Thus, the displacement field of buried faults are smoother and lower amplitude versions of those for faults that reach to the surface. Now, the question comes why displacement fields of buried faults are smoother and lower amplitude versions of those for faults that reach to the surface. So, if you look at this particular figure, you can see the amplitude, the maximum amplitude is around this much, which is less than 0.4 around. And if you look at this one, it is the maximum amplitude is around 0.5. So this is smaller and the curve is also kind of smoother. So this basically happens because of the two reasons. One is a buried fault is, because we are talking about a buried fault. So the buried fault is further away from each point on the surface, and the higher spatial frequencies, or you can say the shorter wavelength in the displacement, decay faster with distance, making the displacement smoother. This is the first reason. Second reason is there is a trade-off between the fault's down dip dimension, that is capital W, and the co-seismic slip capital D, and one is often assumed to determine the other. Now let's look at the static displacement due to slip on a fault, and we are considering the example of dip slip fault here. And the figure here, this figure, this one and this one, the figure shows the vertical component of the static displacement as a function of distance from various pure dip slip faults. And here if you will look at it, this is the fault, this is again the dip slip fault, but it has the vertical slip. That means the slip is almost vertical like this. So the solution for the vertical slip looks like a strike slip solution turned vertically. So if you will look at this one, this is for the strike slip fault, the displacement, this is the strike slip fault, and this is the one that we were just talking about, that one is having this kind of shape. So that means you have just turned the strike slip displacement vertically. That is what they are saying. So the solution for the vertical slip looks like a strike slip solution turned vertically. Likewise, if the slip is not vertical, that means it is something like this maybe. Okay, so in that case, for non-vertical dip, the displacement varies in magnitude as well as sign across the fault. So you can see here the magnitudes were almost same, but in this case here it is kind of higher than this one, and their sign is also different. Now let's talk about the buried fault, or you can say the blind fault, because this fault it is not having any expressions on the surface, so it is buried, and sometimes because it is not visible on the surface, we sometimes call it as a blind fault as well. And this is the example of a blind thrust fault, and you can see the amplitude above the thrust fault is higher. So you can see the amplitude here is higher above the thrust fault, and here in this direction, in here it is lower. So the amplitude above the thrust fault is higher on the hanging wall block. And here let's talk further about the blind fault. A fault that does not reach the surface, the displacement is both reduced in amplitude and varies more smoothly with distance than it would for a fault extending to the surface. Such buried dip-slip faults are sometimes called blind faults because they do not appear at the surface and may not be recognized until an earthquake occurs. So there is one example of blind fault that basically considered to be responsible for the 1897 earthquake happened in Assam, or Shillong earthquake, and it was of very high magnitude, around 8.5, and lot of devastation occurred in that region due to that particular earthquake, and that earthquake is considered to happen on a fault that is known as Oldham fault, which is a blind fault. Now let's talk about the non-uniqueness of geodetic determination of fault parameter. Obviously, we can use geodetic data to estimate the fault parameter, and when you are estimating the fault parameter using the geodetic data, it is considered to be an inverse problem, and this inverse problem is very non-unique. That means it has many solutions, or you can say the many combinations of the fault parameters can have similar deformation. So basically, if you take an example of Tango earthquake, for which we have 6 solutions. So like this solution, this is the model, this is another model was proposed, and this is the third model, this is the fourth model. And in these models, if you will consider if you try to find out the deformation that is on the top here, then the deformation is almost kind of same, but the models are different. So that means the solution is not unique, it is non-unique, because all the 6 models are able to satisfy the need of the data. That means they can produce the same amount of same pattern of the deformation by all those 6 models. So this is called non-uniqueness. So basically, if we talk about the model 1, the model 1 is an infinite fault with uniform slip at depth. Model 2 is an infinite fault with slip tapering at 0 at depth, and model 3 and 4 are finite fault with uniform and variable slip respectively. Model 5 is little complicated in that it assumes that the material near the surface is weaker than the further away. So all these models, if we take into consideration, all are basically able to predict the similar deformation, and we don't know which one is the correct model. So this is called non-uniqueness. Although the geodetic data can be used to find out the fault parameters, and if you will use these data in conjunction with some other data, then you may possibly be having a relatively better solution than the non-unique one. The summary of today's lecture goes like this. Static co-seismic displacement contain 1 by r square term compared to 1 by r term for the propagating waves. Thus, it decay more rapidly with distance from the earthquake. For infinite length fault, the fault parallel displacement in x direction uy varies with distance from the fault y, as uy is equal to plus minus d by 2 d by pi tan inverse y by w. For finite length fault, the displacement tapers off rapidly past the fault ends. If a fault is buried and extends from depth small w to depth w, so we were talking about the buried fault and it is having a depth of small w, then the displacement can be given by from this expression. A fault that does not reach the surface, the displacement is both reduced in amplitude and varies more smoothly with distance than it would for a fault extending to the surface. Estimation of fault parameter using geodetic data is an inverse problem and has highly non-unique solutions. This is the references for today's lecture. Now we will meet for the lecture 3 of module 10. Thank you so much. Bye-bye.